You have been told that smaller transistors mean faster, cooler chips. That marketing promise relies on a simple equation: less space equals more speed. But recent physics research reveals a brutal contradiction where shrinking below 10 nanometers actually degrades performance and floods the chip with heat. This is not just an engineering challenge, it is a fundamental wall in how silicon works. Today, we follow the hard limits of quantum mechanics that force the industry to abandon pure size reduction for new architectural solutions like advanced packaging and chiplets. For decades, the story of computing has been defined by Moore's law: make transistors smaller, fit more on a die, and gain speed without burning extra power. This worked beautifully from vacuum tubes down through centimeter-scale silicon wafers to today's nanometer processes. The logic was sound because electrons behaved predictably as they flowed through channels we could control with voltage. However, the physics of that era relied on classical drift-diffusion models where thermal energy and electric fields kept carriers in check. When you shrink a transistor gate below 10 nanometers, you are no longer dealing with simple liars. You are entering a realm where quantum mechanics takes over from thermodynamics. Recent first principles research by Chen et al. Provides critical evidence for this counterintuitive reality, specifically regarding sub-10 nanometer 2D field effect transistors. The study identifies a hard physical crossover at approximately 10 nanometers that marks the end of an era where shrinking was always the answer. At this scale, reducing channel length further triggers quantum tunneling dominance over classical thermionic emission. This shift means electrons can simply tunnel through barriers they should not be able to cross, effectively bypassing the gate's control entirely. While this mechanism theoretically overcomes Boltzmann tyranny to improve switching efficiency and isolation, it simultaneously causes severe leakage currents that make transistors difficult or impossible to turn off completely. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The consequence of pushing transistor geometry below 9 nanometers is a fundamental alteration of carrier transport mechanisms. The industry targets 2 nanometer nodes today, yet the evidence suggests this introduces unmanageable leakage that undermines the benefits of size reduction. When electrons tunnel freely across the channel, even when the device should be in an off state, power density spikes dramatically without any increase in useful work. This results in increased heat generation and thermal dissipation issues that physical shrinking can no longer manage efficiently. The very act of making these components smaller creates a paradox where performance degrades because energy is lost to leakage rather than being converted into logic operations or processing speed. This physical reality challenges the industry's traditional reliance on shrinking geometry, suggesting that continued scaling below 10 nanometers yields diminishing returns or net performance losses for single-die designs. We are seeing a clear statistical trend. At sub-10 nanometer channel lengths approaching the 2 nanometer target, transistor operation shifts from classical drift diffusion to quantum tunneling dominance. This breakdown of Boltzmann tyranny leads to uncontrolled leakage currents that degrade performance rather than improve it. The heat generated by these leakage paths becomes a critical bottleneck for AI chips and high-performance computing, where power density is already pushing the limits of cooling infrastructure in data centers. Because we cannot simply shrink further without breaking the physics of silicon, the engineering focus has pivoted to what is known as more-than-more innovation. This strategy prioritizes interconnect density and yield over raw transistor miniaturization by combining smaller dies rather than trying to build one massive monolithic chip. The industry's pivot to strategies like chiplets and advanced packaging is a direct response to the physical limits of single-die scaling that we just discussed. Instead of fighting quantum tunneling on a 2 nanometer canvas, engineers now stack multiple specialized chips together using high-bandwidth interconnects. This allows them to maintain small feature sizes in critical areas, while avoiding the leakage penalties associated with shrinking an entire die below 10 nanometers. The implications for manufacturing and supply chains are profound. Advanced packaging requires new materials and bonding techniques that differ significantly from traditional photolithography used in fabrication plants. It shifts the bottleneck from pure wafer density to interconnect yield and thermal management between stacked layers. We must now consider how these quantum effects manifest in commercial silicon-based 2 nanometer processes, or how advanced packaging can practically compensate for leakage, induced inefficiencies in mass production. The gap remains in data regarding whether current monolayer PTWC2 configurations used in laboratory settings will translate to the robustness needed for consumer electronics, but the direction is clear. Size reduction alone has reached its physical limit. This shift redefines what we consider a breakthrough in computing power. It moves the conversation from simply counting transistors on a die to measuring how efficiently those transistors can be connected and cooled as a system. The challenge now involves managing heat dissipation across heterogeneous stacks while maintaining signal integrity at speeds that demand nanosecond precision. We are moving away from a world where every millimeter of silicon shrinkage equals progress, toward an era where the architecture of connection is just as important as the size of the individual components driving them. The story of computing has entered a new chapter defined not by shrinking lines on a wafer, but by how we assemble those lines into functional systems that can handle the heat and leakage inherent to quantum physics at scale. The future belongs to engineers who understand that sometimes making things bigger in terms of system architecture is the only way to keep them smaller in terms of physical footprint while maintaining performance. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.